My dear student, colleagues, and all the viewers who are watching this program live from Facebook page and YouTube channel, I would like to welcome to you all to our International Physics webinar. So, good evening to all here in Bangladesh, and very good morning to all those who are watching this program live from USA. I hope you are well and safe from Corona pandemic. So, as we know that we are staying in a Corona pandemic situation, this is the new type of experience we are having. So, we have to follow the health rules. So, we cannot continue our normal academic program inside the campus. So, we have to start our online program. I think you have already come to know that the Department of Physics, Pabna University of Science and Technology, has started its online program, including online international physics webinar. And I'm happy to share with you all that we have successfully completed our 191st international physics webinar. Today it's our 192nd international physics webinar. And today we would like to welcome you all to a joint session between our Department of Physics, Pabna University of Science and Technology, and the Department of Physics, Rice Center for Quantum Materials, Rice University, USA. And we have with us here today Dr. Kaden, Hazzard, Assistant Professor, Department of Physics, Rice Center for Quantum Materials, Rice University, USA, and he has already connected with us. So I'd like to welcome our speaker. Sir, good evening and good morning to your part. So thanks for accepting our invitation, and thanks for giving us this opportunity to attend such an important webinar with you. And before going to you, I would like to inform all of our students and viewers that we have divided our webinar into three parts. First of all, we would like to introduce shortly our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion session. In that time, anybody can join with us. So I think you have already come to know the title of this today's international physics webinar. That is the ultra cold matter from new phenomena to quantum technologies. And our speaker is Dr. Kaden Hazzard, Assistant Professor, Department of Physics, Rice Center for Quantum Materials, Rice University, USA. And we can see Dr. Kaden Hazzard is a physicist interested in understanding quantum behaviors through a mix of mathematical analysis and computational modeling. Some of the most exciting behaviors may lead to new materials or quantum technologies that surpass their classical counterparts, such as quantum sensors and quantum computers. And we can see that he has completed his bachelor degree in physics and math from the Ohio State University, and his PhD degree from Cornell University Graduate School in 2010. And then he worked as a senior research associate, as a postdoctoral fellow, NRC fellow, SRF, University of Colorado. And then he joined as an assistant professor at the Rice University in 2014, and still he's working there. So thanks again, Dr. Kaden Hazzard sir, so for accepting our invitation. It's a great opportunity for our students to know about the ultra cold matter and about the quantum computer. And so thanks again, and it's your time. You can start your session.
So thank you so much, Pretam, for the very nice introduction there. It's my pleasure to be here and get to share about my research field of physics with you. And in fact, that's really what I'm trying to concentrate on. You know, I could spend all day talking about my research, but most of this talk is about the field in general and about just an introduction to why we're doing the things we're doing. And so, I'm really looking forward to interacting with some people that I don't usually get to interact with. It's of course a difficult time, and it's a shame that interactions have to be online, but it's opened up a lot of new possibilities for getting to meet new people. Yes. So you to ask any questions during the talk, send them to Pretam, and we will talk about them at the end, or if there's something urgent, we can always pause and clarify. So the talk is about this field of ultracold quantum matter. And so I'm going to tell you a little bit about ultracold and quantum, really what are those two things doing together and what can we do with these. And there's a lot of fundamental science, which is mostly what drives me, but there are clear routes that this is leading to some new technologies. So just a little bit more about me. Just to be clear, I'm a theorist. I'm going to talk a lot about experimental research, but I'm a theorist and manager of theorists. I have many good grad students. And before I get into the details of my talk, I thought I should at least show my graduate students, who are really the ones that do all the research and advance things. And so I'm lucky to have a fantastic group of lots of people here, and many that have come and left the group that unfortunately, I didn't have space to include their pictures on. But just because they're not currently in the group doesn't mean they weren't important as well. So the large driving part of why I do this research, other than the fact I get to work with lots of really interesting people, is that the quantum many-body systems end up being really fascinating, leading to new behaviors that you wouldn't expect, and new behaviors that can have these robust applications. And so the first part of my talk is going to be telling you about quantum many-body physics in general. And I understand that some of you are young students and may not even have had a full quantum course yet. So I will try to give you a sense of why these features of quantum mechanics lead to new interesting things. And sort of to start that journey, the first thing I want to tell you is that, you may think quantum many-body physics, this sounds like a very advanced, very maybe exotic thing if you haven't thought too much about it. But it's really related to things that you see in everyday life. So if you look around you, I've got some, I've got water in one of my cups and coffee in the other cup. But anyway, so there's water in this cup, just like we see on the screen. But water has these two profoundly different phases, more than two actually, but two that I'm showing here, water and ice. And they behave in completely different ways, even though they're made of the same stuff. And so this is something that would have been apparent even if you, went back and saw like a caveman, right? So a prehistoric person would be able to tell that it's okay to walk on a lake when it's frozen, but not when it's unfrozen. And so even though that's apparent, it turns out this is a mystery that is extremely deep, and only really in the last 50 years have we clearly started to understand such topics. And there are other things. There are other phases of matter, not just waters and liquids, but actually something like metals are a different phase of matter entirely than an insulator would be. And so there's this question of why are some things insulators, some are metals? Why are some solids? Why are some liquids? Why are some magnets? Some are not magnets. And these are all kind of different phases of matter with different properties. And we have to understand what's going on there. This is our goal as scientists, to understand the world around us, the natural world. And so we should be doing that. So this in and of itself doesn't necessarily look quantum mechanical, except it turns out that to understand some of the very simple looking things here, like this iron, this metal, or a magnet, or I didn't mention it, but if you can have insulators and you can have conductors, but you can also have superconductors, which I'm showing a picture of up here in the upper right. And all of these things, to even get a very basic understanding of them, you really have to use quantum mechanics. There's no way around it. There's no simple way to understand why these phases occur without bringing quantum into the equation. And so that's really what my research is about. So all of these things that seem interesting, it's interesting that we have these different phases. There's scientific mysteries about them and potentially useful. Hinting at this, there's a superconductor. That means, among other things, that it conducts with but as good as anything can conduct. Let's say it's a perfect conductor. So that certainly sounds like it should have applications for power transmission or for levitating trains by making giant electromagnets. These are all things that people talk about. So we want to understand these, and we need quantum mechanics. And if you are coming from certain areas of physics, you might say, well, this is a solved problem. If you look around the world around you, it's all just governed by Schrodinger's equation. We have a theory of everything, and you don't need to understand what these equations are. I'm just putting them up for sort of completeness, but this is Schrodinger's equation of charges interacting with each other, and these that's it. So actually, if you look at all the matter around you, as long as you don't have something radioactive sitting around you, this is in fact the theory of everything. So it's the theory of almost everything is how I've described this. And this is the question is, how can we solve this, right? So this is, even though we know these are the equations, we still have to solve these equations to understand these scientific mysteries. And that's not so easy. So I think that Feynman, in his sort of, characteristic way, said this most clearly. He said, today we cannot see whether Schrodinger's equation, the equation I just showed you, contains frogs, musical composers, or morality, or whether it does not. And so the point being that there are all these everyday things that we believe we have our theory governing them, that governs the world around us, but we have no way of solving it and seeing how these things emerge. And so this really is what we're trying to get at. We're trying to get at, can we understand, using the laws of quantum mechanics, why the world looks the way it does? And so you might say, let's simulate this Schrodinger equation. Right, so we have some equations. Maybe you can write down an analytic solution, right? I can write down some formula that would solve it. That turns out that's very complicated, and we know very few cases that we can actually write down analytic solutions for when you have lots of interacting particles. So you might say you would just solve it on a computer. But it turns out this is also hard. And this is something I'll come back to and explain a little bit about why it's hard later in the talk. But for now, just trust me that it's really, really hard. And what happens is that the computational power needed to simulate a quantum system grows exponentially with the system size. And this is different from classical systems. In classical systems, the power grows as the system, the computational power required grows as the system size grows, but not exponentially. That's really a feature of quantum mechanics that makes life difficult here. And to give you some example of how challenging it is, there are problems that thousands of people have spent lifetimes working on. Chemists, for example, really want to understand molecules, and small molecules are the easiest molecules to understand in some ways. And so one of the smallest molecules you can imagine is a diatomic molecule, chromium-2. And yet, I am showing you many state-of-the-art chemistry methods of the energy of a chromium dimer as a function of the bond length of the chromium dimer. And you see that those curves don't lie on top of each other. That's what you're supposed to take home. That even though this is just two atoms, we are not very good at predicting what the shape of that curve is. And that governs everything we care about for the chromium dimer, right? If I want to know how far apart those two atoms are, how does it rotate, all these things, I have to be able to calculate curves like this. So this idea that things get hard when you go to big systems, well, you don't actually have to go to very big systems. Two atoms is enough to cause problems. And so chromium is a special case. This is probably, among the most difficult diatomic molecules you could pick. But nevertheless, the point is that there are some things that just putting the equations of the electrons in and asking how the electrons rearrange around the nucleus is not such an easy problem to solve. Okay. So we've got to come up with new ideas. We've got to come up with new algorithms. We've got to come up with, really tackle these challenging things. And there are much more interesting things that seem to come out empirically. We have some understanding of these, but certainly experimentally, these are well established. New things come out of us not being able to solve these systems, or at least things we hadn't. What I should say is that things we hadn't predicted actually emerge out of these things, out of systems where that look very interesting. So I'm going to put just 3 examples on the screen here, and I'm not going to go into detail about exactly what these things mean, but I will try to give you a little bit of an idea, and later I'll come back to this again and go a little bit deeper into it. So the first example I want to tell you about is what I've labeled as fractionalization. And actually, maybe I'll just stick with this example. It's one of the most exotic things you can imagine. So fractionalization, what it means is that you have a collection of particles. In this case, it's a bunch of electrons in that little solid that I've got on the screen there. That's gallium arsenide. And there are a bunch of electrons floating around in the gallium arsenide. Now, the strange thing is that there are ways of determining what the charge carriers are in the system, right? So maybe in your freshman physics class or in your electromagnetism class, or at some point, you've seen that you can determine the charge of a particle by applying a magnetic field and a voltage across it and seeing what happens to the current, or applying a current and seeing what happens to the voltage. This Hall effect gives you a way of determining the charge of charge carriers. Now, when you go and actually ask what is the charge of the charge carriers in that material, the answer, under the right conditions, comes out to be exactly 1/3 of an electron charge. And this is extremely surprising because there's nothing moving around in this material other than electrons. So how can you go do a measurement and see it behave as if it's a bunch of non-interacting 1/3 electron charge particles? You know, you think quarks or something, but there are no quarks just running around this material. And so what's actually happening is that the electrons are all moving together in a specially correlated way. They've choreographed a dance to all move together in a way that these collections of kind of a mole of particles, 10 to the 20 particles, are moving together to behave just as if it had 1/3 of an electron charge. And so I think that is incredibly remarkable, right? This is not something you would have expected. It shocked the community when people saw this experimentally. And at this point, we now have some understanding of this, but at the same time, it's very much a frontier research area. And it's the kind of thing that is studied heavily to this day. Okay, so that's one example of the surprises that go beyond even, so we talked about solids and liquids and gases. We all know those phases of matter. Conductors, insulators, superconductors, those are different phases of matter. Magnets, but then there are these really exotic things. And what this points to is that there is matter that behaves according to entirely different rules than we are used to, right? So under those conditions where I have this fractionalization, that gallium arsenide is behaving nothing like a collection of electrons in any ordinary sense that we had understood previously. And that suggests there will be new applications. So if the materials scientists have a set of rules that all ordinary matter obeys, and you come along with a material that breaks all of those rules, there's a good chance this could lead to applications. And so I'm not going to go deep into a lot of these applications or any of these applications, but that's sort of the spirit here, that if we can find new fundamental behaviors, they can lead to applications. And in many of the cases, we do actually have examples. So one of the interesting ones here is, for example, topology. So topology is closely connected to fractionalization. So topology is this mathematical subject of donuts looking like coffee cups. Can you continuously deform one object into another without ripping or tearing it? And we know that you can do things like build more advanced computers if you're able to have the right types of fractionalized systems. So you could build quantum computers which would be able to solve some problems exponentially faster than an ordinary computer. And I'll hint towards that at the end of the talk, although not to the connection with fractionalization. But so anyway, so this hopefully just motivates you that there's a lot of new things that can lead to new applications. I've drawn some historical applications. These are not new applications by any means. These are applications that we now understand and have been around for a few decades. But you know, if you had room temperature superconductors, you'd be able to levitate a train, right? And there are certainly electromagnetically levitated trains that rely on this to reduce friction. If you've ever been in a MRI machine, this relies on superconducting magnets as well. And lasers are fundamentally quantum mechanical. Your GPS system, the global positioning system, this that you may have in like a smartphone, this is something that relies on atomic clocks, which are fundamentally quantum. So all of these things, which are in many ways, you know, things of everyday life, are actually connected to these very fundamental quantum mechanical things. Okay, so that's, I've just told you these as facts. Now I want to try to give you some understanding of this. Before getting into my field of research, I want to go back, especially because maybe some of you haven't thought a lot about quantum mechanics. And so I want to think about why are these quantum many-body systems leading to such useful behaviors or such bizarre behaviors? And the reason, whoops, I lost my clicker. There it is. So the reason it takes a little bit to get to, but it starts with basically a couple simple concepts that I'll explain to you about quantum mechanics. So first, before we get to that, I need to tell you just sort of what is quantum mechanics, where is it valid? So quantum mechanics rules when things are small or when things are really cold or low energy. When I say cold, low energy, I mean the same thing. And there was really this ensemble cast of people here. Maybe you recognize one or more of them. I hope at least one of them that helped develop this theory of quantum mechanics. And one thing that jumps out at you is that if you look around you, the world doesn't seem very quantum mechanical. So I don't see famously cats that are simultaneously dead and alive. This was Schrodinger's cat, this thought experiment that why don't we see this? If you had quantum mechanics, you're supposed to be able to put things in what we call superposition, simultaneously dead and alive. But I mean, it's clear from those words that, what does that even mean? But quantum mechanics tells you what it means. But we don't see that when we look around. So there's something mysterious, again, about the collections of large objects and what happens and why we don't see that. But anyways, these folks worked out the theory, which has been tested incredibly precisely to many, many, many decimal places, 10, 15 decimal places, well, 13 decimal places in many different types of systems. So we know that at least for small and cold systems, it works incredibly accurately. And the key to understanding then where all of these interesting properties and new types of behaviors come from can be understood in the cartoon I'm going to provide you on this slide. So this is a schematic where I think that we all have some exposure to the idea of quantum mechanics of atoms, that atoms have energy levels, and these energy levels are associated with spectra, like I'm showing at the bottom right here. And so just if you can understand that, a lot of the other mysterious properties can kind of be made more intuitive. So first, let's think about what is special about quantum mechanics and how is it different from classical mechanics. So if you look at classical mechanics, that's here on the left. You have like a rocket, let's say, or a spaceship that's orbiting the Earth. And if I apply a thrust, a delta V, to my rocket, I can change the radius that I'm orbiting the Earth at. Right? So if I apply thrust in the right direction, I'll go from a small orbit to a big orbit. And I can pick any orbit size that I want. I can make a little change or a big change, just depending on how much thrust I give to the rocket. And that is precisely the difference of quantum mechanics. So in quantum mechanics, you cannot pick any orbit size. The only possible orbits are at these discrete values that I've shown over here. So if you're in one orbit, you cannot just increase the orbit radius a little bit, but you have to go out by a finite chunk. And that's what gives us these different energy levels that you see in a hydrogen atom, for example, or in any atom. And you can understand this by realizing that what quantum mechanics is saying is that particles actually have wave-like properties. And those waves, which are drawn here, have to have an integer number of wiggles as you go around the orbit. So in other words, if I think about this wave going up and down, it has to come back to the same point it started at. And that requires that you have an integer number of wiggles as you go around. And so that's why the orbits radii are discrete, because I can have one wiggle or two wiggles, but I can't have 1.5 wiggles or 1.1 wiggles. Okay, and so I think this is something probably most of you are familiar with, and if you understand this, you can start to get a lot of intuition for what we're seeing. And before I take you and show you more stuff, I just want to show you a pretty picture. So this is actually a periodic table of all the spectra. Right, so people in my field of physics, which I'll tell you about, atomic, molecular, and optical physics, spend a lot of time measuring spectra. And really, historically, here is just a beautiful collection of very accurately known spectra. They reveal a lot about quantum mechanics, and lots of what we understand about quantum mechanics was first tested and first motivated by these sorts of measurements. Okay, but that's just a pretty picture. Let's go back to the story. So I told you that quantum is all around you, and I gave you some examples. But now let me be more concrete about this. So you're literally breathing in air right now. I know there's air around you. And Air is made mostly of nitrogen, which is a diatomic molecule. This nitrogen can stretch and it can go around in circles. It can rotate. And if you go and classically ask, how much heat can a system hold? If you were to include these rotations and vibrations like this, you would predict a lot more heat could be held in air than actually can be, by a factor of 2 or so. And the reason is quantum mechanics. So if you're to predict it classically, you would get that the heat capacity, the amount of heat that this can hold, is one value, but it's totally wrong, because even in this everyday conditions, I said you were supposed to be cold and small, but this is not very cold and small, and we're already seeing those effects of the quantum mechanics. And as you get colder and smaller, the effects become even greater. But here it's not only detectable, it's a big effect. You can't understand even crudely, air without understanding quantum mechanics. Another example is here in these solids. I'm just showing you an image that was done. I think this is a scanning tunneling microscopy image. The height on this image is the electron density on the surface of a nickel silicon alloy, I believe. And so what you're actually seeing there is where the electrons are sitting in the material. And so clearly the behavior of this solid is being influenced by how those electrons are arranged. And we are now at a point in our technologies that we can start to see some of these things. Okay, and so that's the everyday stuff. The not so everyday stuff, I showed you a little bit here. So I will just, I mentioned the trains and the MRI machines. There are also things like magnetic field sensors, what's called a squid, that we could talk about, but I'm just gonna go over that and show you something that's also not very everyday, but it's pretty cool. Maybe I can't do this. It was just a little video. So I will just show you the still from the video here. This is a frog. This is a frog that's levitating, because if you put a frog above a superconductor, the frog has hemoglobin, I think, in his blood, or for some reason it's anyways, for some reason it levitates. It's just a cute application by actually a Nobel Prize winner, Andre Geim, who thought, let's levitate a frog using this technology. So I like to show it that you can just do things for fun as well with all of this. So I've told you about the truly bizarre stuff, and so I'll skip really over this. This fractionalized material is something that we can begin to understand using some of these ideas of this robustness. So actually, let me take a step back. Let me go back to this idea of the squid. So this picture on the bottom left, this is the squid, a superconducting quantum interference device. This is a way of detecting magnetic fields. And the reason it works is because it's very robust in a sense. It's sensitive to some things in a very precise way. And you can understand this robustness by the same picture of that we talked about for atoms. So just like we said atoms had to have an integer number of wiggles in their orbit, here is a engineered material that somebody has etched this material. It's about 2 microns, so small but very big for a, compared to an atom. This is thousands of times bigger than an atom. And it has similarly robust energy levels for the same reason, that when the electrons move around that 2 micron big loop, you have to have an integer number of wiggles. And so that leads to this application of being able to sense magnetic fields in a precise way. And the fractionalization, I had mentioned this before, that I said you got 1/3 of an electron charge when you did this, when you did experiments on this and measured the electron charge. But actually, these when I said 1/3 of an electron charge, this is not like approximately 1/3 of an electron charge. It is incredibly precisely 1/3 of an electron charge. So it's not 0.32, it's not 0.332, something like this. It's actually 0.33333333333 to something, I think it's 12 decimal places, a lot of decimal places. It's really precisely 1/3. And so you can ask, why is it so robust? Why is it so unable, why is it at exactly that value? And if I perturb the material, if I add disorder or something, why doesn't it change that value? And a big part of the reason is precisely this robustness of orbits. That if I change that I can only change the orbit by discrete amounts. Okay. And so it's a little bit deeper than that. Of course, there's more to it than that, but I think that gives you a good intuition for how you can get robust phenomena from quantum mechanics. And this also starts to give you some intuition, using the example of the superconducting quantum interference device, of how robust behaviors can give rise to useful technologies. So this robustness of orbits leads to robust behaviors, which let you build robust things for applications. Okay, so I hope I've motivated you that quantum is around you. It gives bizarre behaviors and given you a little bit of intuition for why, how to understand some of these bizarre behaviors from this robustness of simple atomic orbits. And so now I want to take the next step and say, well, actually, quantum is hard to understand. And I said this earlier. I said it was hard to understand, but let me try to give you a little bit more about this, right? So here is the sort of monster in the room. This is a werewolf I'm putting on here because this is scary. As a theorist, you want to be able to calculate things, and it turns out it's very difficult to calculate things here. And you can get some intuition again for why. So what I'm showing on this slide is I'm showing some particles. I've got 50 of them lined up there, so 7 by 7 with one hanging off the edge. And let's just pretend that you could simulate those 50 particles on this supercomputer I'm drawing here. Okay, so if I can do that, the question I want to ask is, what happens when I add just one more particle? Okay, now if I add one more particle, that particle can be in different places, or it can have different internal states. So there are a lot of different configurations that extra particle can be in. Let's be really optimistic and assume that extra particle only had 2 places it could be in. Right? So if it only had 2 places, then presumably the number of configurations I have to think about is twice as large as it was before. And so instead of needing one supercomputer, I add one particle. You see how it changed on the left there? It barely changed, right? I went from 50 to 51 particles, just one little thing. But there are now twice as many configurations to check. So actually I need 2 supercomputers to go and understand the physics. And okay, maybe I can get 2, but now I add a third particle, a second extra particle, a third particle, a fourth particle, and very quickly you see things are out of control. That once even if I could somehow understand 50 particles, by the time I get to 56, it's just an impossibility. It grows too much. And in fact, simulating a 300 particle system, if you wanted to do it in this kind of way with classical computers, just simulating 300 particles would require, if you put 1 bit, so one or 0, a binary bit on every atom in the universe, it would not be able to store the state of your system for just 300 particles. And we know matter is made of a lot of particles. So this is really a big reason that these many-body quantum systems are hard to understand. Now, you might look at this argument and say, I didn't actually mention quantum mechanics here. So it looks like I've said classical systems are hard to understand as well. But for interesting reasons, which I'm happy to discuss more about later, classical systems turn out to be easy to simulate. There's a trick to simulating classical systems that avoids this exponential scaling. But as far as we know, and we're pretty sure about this, there is no such trick for quantum systems, and this exponential scaling is intrinsic. So that makes our life really challenging to understand. Okay. So on the next slide, I would just, I wanted to make the point that each of these dots I'm showing you, this comes from a calculation that a student of mine did comparing with some experiments. So each of the dots is each of the dots is experimental data point. And you can think about this solid line came from a bunch of theoretical calculations, and each sort of point for the theoretical calculation is thousands of computer hours. And we were quite clever about how we did this. So really getting and these were for small systems of something like 8 particles. So it really can be incredibly challenging to solve these things. So how are we going to solve the problem? If we can't solve it using normal computers, an alternative route is to use a quantum computer or to use a quantum machine. So you use a device that's unlike your laptop. It's somehow really exploiting quantum mechanics in a way to solve these problems. And this is a huge motivating factor for my field of research. So a lot of my life is spent trying to take one system that I care about. For example, maybe there's this system here on the left, and what I do with my friends, I'm a theorist, so I don't do anything myself, but I talk to my experimental friends, and they do these heroic experiments to build something that realizes the same mathematical model that the system on the left did. Right? And because it realizes the same mathematical model, now we can explore that behavior in a new experiment. And you might think this is totally just a meaningless thing to do, like a stupid thing to do, because you already had the original experiment. Why build another one? But the point is that these new experiments that we build, like here on the right, these new experiments are actually the much more tunable systems to work with. You can do things with them that you couldn't do in the original system. So you can see individual particles more accurately, or you can push on them and see how they respond in a way you couldn't in the original system. And by being more tunable and more measurable in some ways, or at least being measurable in different ways, this actually gives you new insights into what the matter is doing. Okay, and so this is what we call quantum simulation. This is a special type of quantum computer, if you like. It's a quantum computer for solving these types of problems. And in fact, you can sort of upgrade these quantum simulation experiments to things that would be a full quantum computer in principle. But I just want to talk about quantum simulation because I also think quantum simulation is the kind of, well, for me as a physicist, the most interesting application of a quantum computer anyways. So the real experiments don't look very much like my simple drawing here. This is a real experiment. What it looks like, this is a manual blocks lab. There are a couple, here are people for reference, so probably grad students or postdocs working on the experiment. And you see a couple tables that are just filled with optics. What's on these tables are, you see these blue boxes. Those are, I think, lasers. And then there are a bunch of mirrors and beam splitters. There's a bunch of electronics. There's a bunch of wiring for electronics you can see. So, so these are, to give you a sense, the experiments I'm thinking of here are big experiments in the sense they fill a room, but they're not big experiments like a high energy experiment, right, where you have a huge collider that costs billions of dollars. So they are sort of still tabletop, literally experiments. There are two tabletops here. And so you can go and in these systems build these designer quantum materials that let you explore quantum matter. And that is my field of research. That is why we work with the systems that we do. And so this is an example of ultracold matter. That's what we use to do this quantum simulation. And what I want to tell you is why we do it with ultracold matter. Why don't we do it in some different material? Why don't we do it in some other engineered device? Why are we doing these quantum simulation type experiments, or why are my friends doing them in ultracold matter? And so to answer that question, I have to tell you a little about what ultracold matter is, right? So I think if you remember the title of my talk, it was Ultracold Quantum Matter. And I've spent a lot of time telling you about the quantum side of things, but now we're getting to the ultracold side. And the real reason is that ultracold matter lets you do incredible things to tune these quantum mechanical systems that you couldn't do in other systems. So ultracold matter tends to be made from atoms. And so it emerged out of the field of what's called AMO physics, which means atomic, molecular, and optical physics. And if you look at, this is sort of a revisionist history. You shouldn't take my history too seriously, but I think this gives you a rough sense of things. So for the first sort of 100 years, couple hundred years of AMO, people spent a lot of time measuring atomic spectra, like these that I was showing you earlier, and molecular spectra, and not just the kind of electronic transitions that you think of here, but really tiny splittings in the lines that come from what we call fine structure and hyperfine structure. So when we look not just at where the energies occur, but how strong are the different lines, we got so much understanding and so much about the details of these different systems. And this was really part of the first quantum revolution, which is what people sort of are now calling the discovery of quantum mechanics. We went from classical mechanics to the theory of quantum mechanics. Now, this was greatly accelerated in the 1960s when lasers came onto the scene. Lasers let you measure these spectra orders of magnitude more precisely than you could beforehand. And you can do really fun things where you not only measure the systems, but you can control the systems. So measurement and control go hand in hand, right? If you're trying to control something, but doing it without looking at it, right? So I turn my head and try to drive my car, that's a very dangerous thing to do, right? But if I have a good measurement schemes, then that goes hand in hand with being able to control the systems well to accomplish the goals I'm trying to. And so people have developed tools to put your atom in exactly whatever electronic state you want, or even in quantum mechanical superpositions, like Schrodinger's cat, of this level and this level. And that was really, lasers are what let us just kind of do that at will. And now we can do that with 99.99% accuracy in many cases. So another big step that followed this then, so I'm going to say the field of AMO started to transition and really became this portion of AMO at least became the field of ultracold matter in the 1990s. And what happened is that we were able to control, before I was telling you we could control the internal states of the atoms, we could control what electronic state they're in. But what happened in the 1990s is we started to control what the motional state of the atoms is, how they move in space. And that's how you cool something, right? Because temperature means, high temperature means you're moving fast in space. Cold temperature means you're moving slowly in space. And so ultracold matter was about how can we make things move more slowly? How can we get them colder? And we got them really, really cold. In the end of the day, we are dealing with temperatures here of 100 nanokelvin, or actually we have temperatures as low as 500 picokelvin. So this is 10 to the 12th of 1 Kelvin, a trillion times colder than outer space. That's how cold these systems are. And this is beautiful for us because what happens is when we get things cold, this is the whole point of the endeavor. When I get things cold, they're moving so slowly that I can image them and I can push on them with light. So once they get really cold, I can manipulate these systems and put them where I can put different atoms where I want them in different motional quantum superpositions of here and there by poking on them with laser light. Okay. And it's a fascinating story about how exactly this was achieved. The way this was achieved might be surprising to you. The way you actually create these systems to make them cold is using lasers, right? So in our typical expectation, lasers heat things up. But through some extreme cleverness, you're able to use lasers to cool things. And this led to a Nobel Prize. So the way that this worked was, if you have particles moving around and you want to slow them down, what you want to do is when an atom is moving in one direction, you want to have it absorb photons from a laser or from a light source that are moving the other direction. And then that will slow it down, right? It'll absorb that photon, lose momentum. The problem is that if I do this, the atoms that are moving towards the laser will slow down, but the atoms that are moving away from the laser get sped up. And so the really clever bit was to realize there's a Doppler shift of light, that the frequency of light depends on whether whether the atom's moving towards the laser or away from the laser. And so you can set things up so that you're only on resonance. You only absorb that photon when you're moving towards the laser. And this slows all of the atoms down. And so that's exactly how this field started to develop and control the motion of these atoms. And then there was one final step, which is just you let things evaporate. Just like your coffee gets cold or your tea gets cold over time, the same thing can happen here. You can evaporate in a controlled way to make it colder and colder and colder. These are in a vacuum chamber. They're not in equilibrium with the air. So you actually just let things evaporate into the vacuum and get them very cold. So nanokelvin temperatures, particles a micron apart, which means you can sort of image them very nicely. And this led to the creation of what are known as degenerate gases. So when you get gases cold enough, the quantum mechanics, even in a non-interacting gas, becomes important. You start to see the quantum statistics, whether they're bosons or fermions. And this was observed directly in 1995 in the formation of a Bose-Einstein condensate by several groups, including one group at Rice. Randy Hewlett's group at Rice in 1995 was one of the first 3 groups to observe this. The others are listed here. And then a little bit later, a few years later, people did this with fermions and made degenerate Fermi gases as well. Okay. And so now, with these ultra-cold gases, you can not only make sort of simple systems like BECs, Bose-Einstein condensates, and Fermi gases, but you can start controlling atoms atom by atom. So this is a picture of what's called a quantum gas microscope from Martin Zwierlein's group at MIT. There are now several other people that have this type of capability, where they load atoms into a regular periodic potential in space, and then they can tell where every atom sits. So the top picture is the actual experimental data. The bottom is what they infer from that graph. And you might question, the top picture looks a little blurry. Can they really tell where every atom is sitting? But actually, it's very, very accurate, with something like well over 99% probability in some of these experiments, I believe. They're able to assign exactly which lattice site the atoms are sitting in. And so you start with this quantum mechanical thing. Remember, the quantum mechanics, the atoms are sitting in a superposition of here and here and here, and all the atoms are correlated with each other. And then you do these quantum measurements and get the snapshots like at the bottom. And so you can tell all about these quantum systems. Not only can we image them, but we can manipulate them and create interesting structures like this. So you can use lasers to put the atoms wherever you want. And this is a picture from Antoine Brouvet's group that shows you can arrange the atoms in an Eiffel Tower. Right? So now you can do whatever you want. You can study interacting quantum matter on geometries that look like the Eiffel Tower, if you want. Okay, so this is the level of control. That's what you cannot do in a real solid, right? If I was trying to take something like my ceramic coffee cup and engineer a new material like that, you cannot atom by atom place things and study the electrons living on an Eiffel Tower. So this is, I hope, gives you a sense of why we want to use these types of systems to do the quantum simulation. I hope I've motivated that the quantum simulation is going to be interesting, that there are all these new behaviors out there for us to explore. And so in the last part of my talk, I'm just really quickly going to overview some of these things and leave time for questions that we can discuss. So maybe the easiest to understand kind of application, or maybe the easiest to understand why it would be important application, comes from putting fermionic atoms into optical lattices. So this is just an artist rendering of an optical lattice. It's just a periodic potential in 3-dimensional space. This is a lattice formed from light. Okay, so this lattice, the way it forms is you send counter-propagating lasers that form a standing wave of light, and then the atoms sit in that standing wave of light. And that's what's depicted here. Now, in the real experiment, it's not exactly a box the way I drew it. It's maybe a more elongated shape. It's but this gives you a sense of actually the typical scale of these systems. They're big, but not huge. It's not, it's not billions and billions of particles. It's maybe at most 1 million particles in here. But this system looks very much like electrons in a solid. So here you have atoms that move around in this potential of light. If you look at the math that describes this, it is extremely similar to how electrons can move around in a solid, which has a periodic crystalline structure. So there's just the Coulomb interaction between nuclei and electrons in a normal solid, and here you have an externally imposed potential from the light that the atoms move in. Okay, so what happens when you study this is that you can see really rich physics. So maybe the most easy to understand physics, or at least easy to describe, again, why it's interesting physics that comes out in a system like this, comes from the field of superconductivity. So there's a dream to get these high temperature superconductors because of the obvious applications in power transmission and room temperature strong magnets that you could create. But they've eluded us. The highest temperature superconductors we've ever found conduct maybe at liquid nitrogen temperatures, but not room temperature. but we don't know if they can go hotter or not. And what's really frustrating is that we don't actually understand the quote high temperature superconductors at all. I mean, many things about them are just totally mysterious to us. So what I'm doing is I'm showing you in the upper right-hand corner, if you've went to enough physics talks, I can almost guarantee you've encountered a graph like this at some point. Anytime you hear a talk on superconductivity, this tends to come up. This is a phase diagram as a function of the temperature and as a function of what we call the doping. So just sort of how many charged impurities are in the material. And you see there's a rich phase diagram. There's what we call an antiferromagnetic phase, which just means the spins, little magnets that live on the electrons, go up, down, up, down, up, down. That's an antiferromagnet. There's the superconductor if I dope it enough, but there are also these things called pseudogap phase and Fermi liquid. Fermi liquids we understand very well. Nobody knows what the pseudogap phase is. This strange metal, maybe you can tell from the name of it that we don't understand what the strange metal is. It has properties that seem to go against anything we understand. So something strange is going on. And some of the most promising attempts to understand this invoke things like quantum gravity, which may sound absurd. Certainly there's not actual quantum gravity going on in this system, but it turns out the math from string theory and quantum gravity can be used to understand these strange metals using the sort of holographic correspondence. So there's a whole story, and you could invite other people to tell you about this story of holographic correspondence math to apply to these systems, but it's one way. People are desperate, right? We're trying anything to understand this strange metal. And this is actually highly simplified. There's several other phases in this phase diagram that I didn't label, or these people that I stole the picture from didn't label. I forgot to attribute who it was, so I forget now. But now in cold atoms, in this optical lattice that I showed you, we have realized very similar physics. When you look at the high temperature superconductors, essentially what it is, it's electrons moving in a two-dimensional square lattice with strong Coulomb repulsion that keeps particles from sitting on the same site. And the particles can tunnel quantum mechanically from one lattice site to the adjacent lattice sites. That is the essential physics of the high temperature superconductors. That's it. Again, we know the Hamiltonian. We can write down a decent approximation of the Hamiltonian, but we can't solve it because quantum mechanics is hard, like I told you. So I said we fight quantum mechanics with quantum mechanics. We're going to use these ultra-cold systems to build new quantum mechanical systems we can probe and tune. And now there has been a wealth of experiments observing this antiferromagnetism, or at least signatures of the antiferromagnetic fluctuations or correlations. We have signatures of transport that look very much like the strange metal, although they are in a quite different regime. So we're learning new things about the transport and the strange metallicity and so on. And so this, again, I could give you a whole talk on the details here, but I'm just, if you want to see some of them, go look at the references that I put up here. This gives you a sense that we are starting to make a lot of progress on this and many other problems, not just high temperature superconductivity, but topological phases and other things using these ultra-cold quantum simulators. And that's where all of my research sits in. My group does many different things, so let me just put up a slide mentioning this. The group does many different things. How do we cool these systems better? How can we use different types of AMO systems to realize physics that was inaccessible before? Things like Rydberg atoms or alkaline earth atoms. We think about quantum algorithms for quantum computers, new numerical methods, all kinds of stuff. But maybe to just connect with the slide I showed you before, I will put up my final slide, which is with collaborators in Kyoto University, Japan. They have realized and I think I'm back. Let me give it just a second. I will wait for Dr. Doss to confirm that. Can you hear me? I'm back now?
Yeah,
Okay.
yeah.
I
You are
apologize for
back.
the internet. Okay, great. Apologize for that. Fortunately, it was on my last
Nice.
slide. It's like it knew it was coming. So our experimental collaborators have achieved the coldest fermions in the universe, 1 nanokelvin. Interestingly, the only way they can do thermometry on this system is by comparing to theory that we is running. It is the coldest place in the universe, the coldest fermions in the universe, unless there's like an alien civilization running ultra-cold matter experiments out there. And so I think this is a good place to stop. I could tell you a lot more about the specifics of what we do, but this is a good example that this is one of these high temperature superconducting analogs, and we're making a lot of new progress that this is going to open up new physics for us to explore. So let me stop there and take any questions that you have. I will just put up my conclusion slide here for you.
So thank you for your wonderful presentation. So we have got few questions. We can start the discussion session if you allow. So the first question: what is the Fermi liquid?
What is the
Fermi liquid. Fermi.
Oh, what is the Fermi liquid? That's a great question. So this comes from this was developed by Lev Landau back in, I think, the 1940s. And the idea was, how do we understand fermions when they interact? So if we have non-interacting fermions, so things like if I just had electrons, but imagine there was no Coulomb interaction between the electrons, or something like this, then what would happen? Well, they would form a gas, and they would form what we call a Fermi gas. And so the issue is that things interact. And so how can we possibly understand this interacting system? I've told you how hard it is. So the fortunate thing is there are systems we do understand, and the Fermi liquid is one of them. And so the Fermi liquid is what happens when you turn the interactions on in a Fermi gas, but it doesn't enter a new phase of matter. So if you take the Fermi gas and look at things with interactions but are in the same phase of matter as that non-interacting gas, that's a Fermi liquid. And so what's pretty remarkable is you can be in that Fermi liquid phase even when the interactions are huge. So you wouldn't think that the effective interactions are small. You can still be in that same phase, and then you can understand the physics by really very similar arguments to the non-interacting phase. So you can kind of do your calculations ignoring interactions and then just add simple corrections for the interactions. And so just at first glance, it's not obvious this should be a good description of a metal. It's not obvious this should be a good description of neutrons in a neutron star somewhere, but in fact, it works extremely well for many cases where you're in this phase of matter. So if you want to learn more about this, you can look at for example, a solid state textbook will have Fermi liquid theory discussion, or if you look at most many body theory textbooks, they will discuss this.
Thank you, sir. We have another question. So can we use ultra-cold matter in quantum computer?
Yeah, so it's a great question, and the answer is yes. Not only can we, but we have people so many of our most promising startup companies, for example, in quantum computing, are based around ultra-cold matter or its cousin, trapped ions. So trapped ions use exactly the same laser cooling sort of techniques, things like this that I described, or they can use these that I described earlier. So they're not quite as cold. They're a little bit different because they are ions, and so they're held in place in different ways than the neutral atoms. But so there's a $2 billion startup company. I'm not even sure if it's fair to call that a startup anymore, IonQ, that's based on trapped ion technologies. Honeywell Quantum Solutions, which is also a very major player, is based on these trapped ion technologies. If you really want to think about the neutral atoms, there are startups in Europe, one called Pascal. There's a startup in Berkeley, California called Atoms. There are many others. So I'm sure I missed somebody saying this, but it's a promising platform, and it's for exactly the same reasons. So to understand this, let me just go back to this, to this picture. So I may have to reshare my screen. Let me check here.
Yeah. Maybe you have stop share, so you have to.
Oop, wrong button. There we go.
So you have to share it again, because maybe you have to stop share.
Can you see it now?
Yeah, can see.
Okay, so I showed you this Eiffel Tower. And so the whole point of building a quantum computer is that you have to have quantum elements, which atoms certainly are, and you have to be able to control them. You have to be able to let them interact and turn the interactions off. You have to be able to control the state. And I told you we could control the internal state of the atoms. And if we can build things like these Eiffel Towers, I didn't mention this, but we can actually move the atoms away from each other and then bring them back towards each other. We can let them interact and turn that on and off. That's exactly, if you look at the programs of a quantum computer, the algorithms, it's things that are a sequence of operations like this. So depending on the context, you might talk about C0 gates or Hadamard gates, but these correspond exactly to physical operations that I'm talking about here. So if you send a laser pulse focused onto one of these atoms, which people can do, that creates a superposition between two states, up and down if you're thinking about spins, or 0 and 1 if you're thinking about qubits, and that is the Hadamard gate. Or if you want to do a C0 gate, that's essentially a gate that takes two atoms, and when they're close, something happens. When they're not, if they're in one state, then something happens. If they're in a different pair of states, something else happens. Right, and so that's exactly, you can do that by interactions, because you can put the atoms close, and if they only interact in one special state, then you're only going to undergo some transformation in that state. So absolutely, there are things like this, and I would say that I talked about quantum simulation. I talked about it in a very analog way, that you just kind of build a Hamiltonian that's the analog of the Hamiltonian you want to study. But there's a whole variety of things you can do that are more programmable and makes it look more like quantum computation. So I think there's a whole continuum of sort of quantum technologies, from very special purpose quantum simulation to fully general quantum computation, and they can all be done in the same system.
Thank you, sir. So we have another question. So I can ask two questions together, very similar. What is the Bose-Einstein condensate, and can a Bose-Einstein condensate help improve microscopy beyond the nanoscale?
Okay, so first off, what a Bose-Einstein condensate is. So we talked about Fermi liquids. Fermi gases are what happen when you take non-interacting fermions and bring them to 0 temperature. Fermi liquid is what happens if you add interactions to that picture. A Bose-Einstein condensate is what happens if you take bosons, the other fundamental type of particle, and get them cold enough. And in fact, with bosons, there's a critical temperature that as soon as you get below that critical temperature, you get what's called a Bose-Einstein condensate. And these Bose-Einstein condensates are what it is, like how you can tell if you have one, is that all of the particles lump together in one state. So they don't lump together in real space. They don't lump together into one position, but they lump together in momentum space. So if you think about the particles as a wave, and that wave's really spread out, it's spread out the whole size of your trap. It's like you put all of the particles into that state where each particle is in a wave spread out over the whole trap. And so this is something that is very fundamental. Many phases of matter can be considered as a Bose-Einstein condensate of something. Sometimes that something is rather abstract. In fundamental physics, you may have heard about like the Higgs boson, right? And so if you look at the universe, it's a condensate of the Higgs boson as kind of our vacuum, right? So this idea of particles condensing is very, very widespread. And you can think about these Bose-Einstein condensates as, in all cases, of being lots of particles aggregating into the same state. And to the second part of the question about whether it can be used to improve microscopy, I think was the question. That's an interesting question, and I do remember 10 years ago, people were talking about doing better lithography and things using a BC maybe as a kind of lens, or but I don't know much about that. But what I can tell you is a slightly related idea, which is the using Bose-Einstein condensates to improve interferometry. So the idea, or to improve other detection technologies. So just like with light, you can put light through a beam splitter. And if you put light through a beam splitter, you can detect phase shifts of the light really well. Right? So now you can do the same thing. If you're in a Bose-Einstein condensate, I said the particles are behaving like waves. And if the particles are behaving like waves, I can put this matter, these atoms, through the equivalent of a beam splitter, let them go around and detect whatever the analog of what would cause a phase shift for the matter. And so you can use this to do precision, and so different things can cause phase shifts of the matter. Rotation is one of these things. So you can actually build rotational sensors with Bose-Einstein condensates that are potentially better than anything else. So there are lots of kinds of, I would say, sensing capabilities with Bose-Einstein condensates, and also with many of the other systems that we work with in cold atoms. But for microscopy in particular, I'm not an expert. I'm not sure. There may be possibilities, but off the top of my head, I don't know. Yep.
Yes, so thank you. This may be the last question. So how can we control short-range interaction in cold molecule collision?
Yeah, wow. So this is a really good question. There's a whole field of like subfield of ultracold matter that is all about controlling the interactions, the short range interactions in atomic and molecular collisions. And yeah, I won't take. I have slides from another talk, but I won't try to find it right now. But so let me try to do this with my hands. So each of my hands is an atom. And now each of my atoms has different spin states it can be in. It can be a spin up or it can be a spin down. Maybe it has more than two, but just imagine it has at least two. Then what happens is, imagine that your atoms were always spin down. They come in, collide, and then they bounce off of each other. Right? And that's the typical collision process that determines how these atoms interact. The interesting thing is that when you get to really short range, so when these atoms are coming in from a micrometer apart and colliding, all the collision physics is more like chemical stuff, right? That's happening at really short range in terms of like 1 nanometer. And at that short range, these other sort of other states, so the state where both the atoms have spin up instead of both having spin down, can become important. So what can happen is they come in, they're spin down, and you're so cold that you have no chance of flipping to spin up. I'm imagining they're in a magnetic field, so you're fully spin down. But when I come to short range, now there are these strong chemical forces, and they can actually mix in quantum states that have the two spins up. So I come in, when they're far apart, I have two spins down. I come in, I collide, and I start coupling the states that have the spins up. And so there's a phenomena in quantum mechanics generally, or scattering in particular, where if levels are in resonance, they have a big effect on your wave function. Right, so this is just like perturbation theory. There's a huge effect when something is right on resonance, and you can't use perturbation theory anymore. And so that happens here too. When this up-up channel is tuned to be exactly on resonance with your down-down channel, you get what's called a scattering resonance. And you can see how to tune it already. If the one channel things interact in has both the spins down and the other has both the spins up, all you need is a magnetic field to tune it, and you can tune these so they come into resonance with each other. And so using this technique, which is called a Feshbach resonance, experimentalists can tune the interactions from zero. They're actually zero crossings, at least for the long range, in technical terms, the S wave low energy scattering length. And you can tune it from zero to infinity. So there's a pole in the scattering length. It diverges to infinity, and you can tune it to either plus or minus infinity. And people have used this to study Bose, Bardeen-Cooper-Schrieffer BCS states, things like this. There's a whole. I mean, that's just one of many examples. Tuning interactions is very important. Yeah, and so that's the most prominent way. There are other ways as well.
Okay, sir. So thank you for your wonderful presentation and nice discussion session. So I think our students and viewers have learned a lot of things about the ultra-cold matter and the exciting things about our upcoming quantum computer. So thanks again for giving us this opportunity to arrange such an important webinar. So I think as our intention or aim is to motivate and encourage our students, I think by your lecture, some of our students are definitely motivated, and they might fall in love in this new research, and hopefully in near future they might join this field in research group. So thanks again for accepting our invitation, and we would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. It's a great day for our department, and it's my honor and privilege to host you in our international physics webinar. So bye for today, and hopefully in near future we will arrange another webinar with you. And after the COVID, I will definitely invite you for a face-to-face, as we discussed earlier, for a face-to-face session, and that will be a very great thing for our student, and we can exchange our knowledge between us by interacting. So thanks for everything, and bye for today.
And thank
Have a
you
nice
very
day.
much for the. Thank you so much for having me, Pretam. It
Yeah,
was
yeah,
great
it's my honor.
getting to know you and discuss with questions. Yep. Mhm.
Bye.
Thank you.